Hello everyone and welcome back. In our last video, we solved past paper questions to target these two concepts. This is a screenshot of Pearson ACE Physics syllabus, and these are the expected learning outcomes for Unit 2, Waves. Today, we will solve past paper questions from the last concept of this chapter, that is photoelectric effect. And I've divided this concept in two parts. First part will target these two learning outcomes. And the past paper questions that I've picked to target these two concepts are here. So all of these questions we have already solved. You should watch my previous videos here. So first, electron volt. You can expect simple questions from this concept, or you might need to use this as an intermediate step to solve some complicated question. But for photoelectric effect, first of all, you really have to understand the general idea of the experiment and its implications. For example, to check your understanding, ask yourself this question: can you write 3 reasons why wave model cannot explain the observations of the experiment? Or do you even know what the observations are? What are the 3 most important observations in the photoelectric effect experiment? This second question also, you just have to discuss whether the student's answer fully explains the photoelectric effect, and you will get 4 marks. So you see, to answer these questions, you don't need any math, you don't need any complicated equations. But mind you, a lot of students think that, okay, this is just a descriptive question. I can write about where Einstein was born and how he came up with photoelectric effect, and I will get these 6 marks. The answer is no, this is not true. You have to write to the point 3 reasons why wave model fails to explain the observations, and then you have to write 3 more reasons to explain why, if we switch to particle model of light, the same 3 observations are very easily explained. Okay, we'll start with this question first, because right now we don't even know what a photon is, right? We haven't discussed it. I'll try to explain the whole concept with 3 simple predictions while assuming that light is a wave. And then we will look at 3 observations in the experiment to test our predictions. And finally, we'll see how the same 3 observations, which we could not and cannot predict using wave model of light, the same 3 observations will be explained if we switch to particle model. So here, you can see these are my 3 predictions. And now I'll explain why wave model would predict these results. So our first prediction is that energy of the emitted electron should increase if we increase the intensity of light. Now, what is intensity of light? You can simply think of intensity as brightness of the light. If you have 1 light bulb, you have low intensity. If you have 10 light bulbs, you have high intensity. Now, what is the reason of this prediction? The reason is that in wave model, energy of the wave depends on its intensity. Therefore, our prediction is that if we increase the brightness of light or intensity of light, the emitted electrons should have higher kinetic energy. Our second prediction would be that there should be some time delay before the electron is emitted. And the reason for this prediction is that in wave model, the energy of the wave is distributed over the whole wave front. So the electron cannot absorb the energy of the whole wave, and therefore there will be some accumulation time for the electron to gain enough energy to break free from the metal surface. Our third prediction will be that the emission of electrons should not depend on the color or frequency of the light that we are using. We can even use light colors, for example, yellow, orange, pink. And because we can always increase the intensity to increase the energy, we can provide enough energy to the electron. For example, if you are using yellow light, you can use 10 yellow light bulbs to increase the energy, and you will always be able to eject electrons. You will always be able to give enough energy to the electron. It doesn't matter which color you are using, as long as you are using high enough intensity. Now, let's talk about observations. So the first observation is that if we increase the intensity of light, the kinetic energy of the emitted electrons does not change. So there goes our first prediction. We did not expect to see this result. And even after observing this result, we cannot explain it using wave model of light. Our second observation in the experiment is that the emission of electrons is almost instantaneous. There is no time delay. And again, we don't know what's going on. We cannot explain this instantaneous emission of electrons. And finally, our third observation in the experiment is that for a fixed metal surface, there is always a specific minimum frequency below which the electrons cannot be emitted. So if your light has a frequency that is smaller than this minimum frequency, the photoelectric effect is not observed. No electron is emitted. And it doesn't matter how much you increase the intensity. If your frequency is below some minimum frequency, you will have no photoelectric effect, you will have no photoelectrons. So the final result of the photoelectric effect experiment is that the wave model of light cannot explain these observations. Now let's see how by switching to particle model of light, we can easily explain these observations. So Einstein proposed that light is made up of packets of energy called photons, and the energy of a single photon will be given by this equation E equals hf. Now h here is the Planck's constant and f is the frequency of the photon. Notice the frequency dependence already. So energy is depending on frequency. A very important thing to remember is that in particle model of light, the electron will always absorb the whole photon. It cannot absorb 1.5 photons or, for example, 2 photons and add up their energies. No, the energy that the electron absorbs will always be the energy of a single photon, and therefore that energy will depend on frequency of light. This point is so important that I want to write it down. Electron will always absorb a single photon. Now let's see how this simple model can explain these three observations. So the first observation was that energy of the emitted electron does not depend on the intensity of light. Now, increasing the intensity of light, which is equivalent of increasing the number of photons according to our particle model, it will not increase the kinetic energy of a single electron because the electron always absorbs a single photon. So if you have 100 photons coming towards an electron, the electron will always absorb a single photon, and the energy of that photon will depend on its frequency. But you should remember that increasing the intensity of light, in other words, the number of photons, will increase the number of electrons that are emitted. But the kinetic energy of a single electron will not increase. So for example, if you have a single photon can only eject one electron from the metal surface. If you have 100 photons, they will be able to release 100 electrons from the metal surface. But do not forget that the kinetic energy of all of these emitted electrons will not depend on the total incoming photons. It will only depend on the frequency of light. The second observation was that emission of electron is almost instantaneous. There is no time delay. Second observation is also justified because the energy of photon is not distributed, right? The electron will always absorb the whole energy and will be released immediately without any time delay. It does not have to wait to accumulate energy. Finally, the explanation for third observation is that if the frequency of the photon is smaller than the minimum frequency, it means that the photon does not have enough energy to overcome the work function of the metal. Work function, if you don't remember, is the minimum energy that an electron requires to break free from the metal surface. So if you don't remember anything about photoelectric effect, make sure you remember these three things. And you have to use these exact words. Energy does not depend on intensity. Second, there is no time delay. And finally, there is always some minimum frequency below which you will not see any photoelectric effect. It doesn't matter how high the intensity is. So these three observations cannot be explained using wave model, but the same observations can be explained using particle model. And now you can easily answer this second question. The student is explaining that light above certain threshold is able to free electrons from metal, which is another way of saying that below this threshold frequency, there will be no photoelectric effect. This was the third observation. Next, we have some of this energy is used to release the electrons. So they are talking about work function. So we can understand this explanation like this. Imagine there is no work function. So the electron is just sitting there. You don't need to break it free from the metal surface. In this case, if an electron absorbs the energy of photon, which is HF, all of this energy of photon will be converted into kinetic energy of the electron, right? So electron will start moving because it was already free. But now imagine that the electron is not free. It is trapped inside the metal surface and you have to pull it out. And in order to break it free, you have to give it some energy. In other words, work function. So the kinetic energy, in this case, the kinetic energy once the electron is released will be smaller than the total energy of the photon that it absorbed because some of that energy was used in work function. So how much the kinetic energy will be smaller than the total energy of the photon? It will be smaller, which means we have to subtract from the total energy of the photon some work function. This is the energy that we used just to free the electron from the metal surface. So that's why the final kinetic energy that the electron will have will be smaller than the total energy of the photon. How much will it be smaller? It will be smaller by the same amount as the energy which is used in work function. And finally, we can talk about electron volt. We know that energy of photon is given by HF, but in the question, we are not given frequency, we are given wavelength. So we need an equation to find frequency from wavelength. We will use this simple equation, C equals F lambda. You can just rearrange this for frequency. Frequency will be c speed of light divided by lambda. Lambda is 700 nanometers. C is the speed of light, which is 3 times 10 to the 8 meters per second. You will get frequency. Once you have the frequency, you can substitute this here and you will see that the energy that you get from this equation is 2.84 times 10 to the negative 19 joules. Now we want to convert this energy in joules into electron volts. And we want to show that this energy is equal to 1.8 electron volts. So electron volt is a smaller unit of energy, and we use it to measure the energy of subatomic particles. 1 electron volt equals 1.6 times 10 to the negative 19 joules. Now that we have this relation, we can make two conversion factors. The first one will be 1 electron volt divided by 1.6 times 10 to the negative 19 joules. And the second conversion factor will be 1.6 times 10 to the negative 19 joules divided by 1 electron volt. So the result that we got for energy was 2.84 times 10 to the negative 19 joules. And now we need a conversion factor. Which conversion factor should we use? We will use this conversion factor, the first one, because it has joules in the denominator. And you see, if we multiply this conversion factor, the joules will cancel and our final result will be in electron volts. So we just have to divide this number by 1.6 times 10 to the negative 19, and our final answer will be in electron volts. And well, you should get close to 1.8.